Today we are continuing our work with exponential graphs, and in the past we were looking at bases that were either integers, or here we have a rational number like 1/4. Now we're introducing a new base called e, and we call it the natural base. It's an irrational number, so the decimal goes on forever without any repeating or any termination, and this number comes from analyzing what happens with growth. For example, growth of your money in compounding interest situations or population growth. So I'm not really explaining where the number comes from, but it's the number that we use, and it has to do with exponential growth because here you have a base raised to some power, and if you are using very large values of x, that means you are applying the growth very frequently because you would have a very large exponent, even though the amount of interest or the amount of growth is going to be quite small with this 1 over x. It would be very frequent, and so we have this trending toward that number. Some of our homework problems have us just using a calculator to get a decimal value. That's what you see here in example number 1. So there's your function e to the power of x, and I'm really just pointing out where it is. You might have a graphing calculator, but if you have a scientific calculator, it is on there somewhere. It's over here on the left-hand side above that natural log button. So if we hit the second function followed by that button, you can see we've got our e to the x there, right? And typing in that value, we would get a decimal. So rounded 3 decimal places in cases like these. So there's a couple of problems of that sort, but we're going to spend most of our time looking at either graphing by hand when we have a base of e, or some of the compounding interest formulas that we'll get to in a little bit. So we are going to again use 2 critical values. We will use 0, 1, there it is, and we'll use 1, the base, and the base is the natural base of e. Now in terms of plotting that point, we're going to approximate that at 2.7. So as we're graphing by hand, we don't need much more accuracy than that when we're graphing. If we're using algebra instead, we'll use 3 decimal places, but that's enough. You can see here we have a few other critical points listed, but in terms of our table of values, we'll just be using these 2. And don't forget that horizontal asymptote as well. We'll be graphing that as well. So again, your domain is all real numbers. Your range is listed there, your y-intercept, so you can take a look at those details. Let's go to our examples. I'm going to turn over to our page 3, right up here at the top. Let's see if we can graph by hand 3 plus e to the power of x plus 2. All right, so that's your k. Notice it's in front. There's your h. If you prefer, you can shuffle those terms around so that you end up with the value of k in the back. You can do that if you like. That's fine. But notice our base is the natural base of e, so our parent function is e to the power of x. So as we are creating our table of critical values, we want 0, 1, and 1, the base of e, which we're approximating as 2.7. Don't forget that horizontal asymptote at y equals 0. So in this case, there's no reflection, there's no stretch or shrink, so we're going right to the translation. We want the h and the k. So here you see the x plus 2, but remember when identifying the h, you always change the sign. It's actually negative 2. We're moving left 2. So we'll take each x coordinate and subtract 2. So we have a negative 2 and a negative 1. As we're moving it up 3, that means the k is 3, right? No change there, still positive. We will take each y-coordinate and increase it by 3. So add 3 to each of these y-coordinates, we have a 4, and then we have a 5.7. The horizontal asymptote is also a value of y, so we need to add 3 to that as well. With that, we have enough to work with our graph here. There's our horizontal asymptote at positive 3. And then plotting our 2 critical points. You can see we do have that exponential growth curve occurring even with that base of e. So it looks very similar to the kind of work we did yesterday. Other details, domain is all real numbers. Our range from 3 to infinity, but not including 3 itself. Horizontal asymptote. And here we don't have a y-intercept detailed from the critical values that we've come across, and we haven't learned how to calculate that just yet. So for this type of a problem, we'll just skip that detail here. We'll only write it down if we actually have that provided on our table. So here's another problem. Take a look at number 3. This time we have negative 2 times e to the power of x. So we're going to have a reflection in this case. So again, we start off with the parent function, y equals e to the x. Here's my critical values, 0, 1, 1, 2.7, and don't forget that horizontal asymptote. We do have a reflection, so let's think about this. What are we going to do with our table of values here with this negative sign? So we covered this yesterday. If the negative sign were on the x, well then you would change the sign on the x's. But here the negative is not with the x, so we don't change the x's, we change the y's. So if you think about what that means, your positive y's are going to become negative y's. So you are reflecting upside down, is what we see happening here. So your x coordinates stay the same, your y coordinates needs their signs changed. We do have a stretch. The value of 2 means it is doubling in height. So once again, we are affecting the y coordinates. So the x coordinates stay the same yet again, and now we'll multiply each of the y coordinates by 2. Now our horizontal asymptote is just a 0, so of course you can't double 0. There's no translation here, so we are ready to plot these points. Notice that we do have a y-intercept identified this time. So our domain is all real numbers. Our range is from negative infinity up to, but not including 0, because the horizontal asymptote is at 0. And this time, as we do have a y-intercept here, we will identify it. There it is. That's one of our critical points, right? So we'll see a few examples in the homework where we're graphing by hand like this. But we also want to take a look at a problem where we're not focusing on the graph, but we're still looking at identifying the kinds of transformations that we have. Do we have a reflection? Do we have a stretch? Do we have a translation? And we want to describe it, meaning we want to detail what that might look like. So here's my for my reflection and my stretch and my translation. Here's my little table to kind of put all the information in one place. The issue here is that the problem they give us is not quite in standard form. Okay, we have the 5 up front, but it can be in the front or the back. It doesn't matter. We know that's the k. That's the vertical movement. The issue has to be with this. We have a base of e raised to that power of negative x plus 1. Now, it looks fine. What's the deal here? Well, we have to have a positive x, and obviously we don't. We have a negative x. And if you've got a negative on the x, you have to first factor out a negative 1. So what that means is we're going to take that exponent, factor out a negative 1, and that means you now have a positive x minus 1, right? So notice how that changes the sign on the h. What we thought was the h is not the real h. This is the real h now. So when we're identifying the h and the k, you can see that inside the parentheses, I have an x minus 1, so you always change the sign to its opposite, so that's a positive 1, so that means we're shifting it to the right. And then, of course, the k is a positive 5. No changes there. If you were to find the h from the original problem, you would think that it might be a negative 1, a left 1 movement. But that's because it's not in the format we need. So factor out the negative sign, so it's been separated from the x, so it looks like x is positive. So we do have a reflection, but we wanted to describe it. The negative is paired up with the x, so our positive x's will become negative x's. So that means my right side will move to my left side as my positive x's become negative. So we're reflecting in the y-axis. No stretch or shrink here. Lastly, the translation, we're moving right 1 and up 5. Next, we're transitioning to those compounding interest formulas. Many of you have seen this before in other classes. It's a very common topic when we're talking about exponentials. And so we have our compounding interest formula, and then we'll also add the continuously compounding interest formula here in just a moment. These are just the details of what all those letters mean. So A is what we're going to end up with, right? That's the amount of money that we will have earned. P is your starting amount. We call that the principal. But you can also think of it like your initial amount. So I'm going to put that word in as well. It's the initial amount. And the reason why that's helpful is because sometimes we will be using formulas that are working with compounding growth, but it's not necessarily money. And so we want other words that describe what we're starting with. For example, if you have radioactive decay, that would be exponential decay instead of growth. But we would not have a principal when working with radioactive material. We would have an initial amount, but it would still be found right here in front. Here for the financial formula, we need a rate. So the R represents the rate. Make sure that you change that percent that they give you to its decimal equivalent. N stands for the number of compoundings per year. All right, number of compoundings. For example, if you wanted weekly, right? Well, that means you would have N equals 52. If you wanted monthly, right, you would have 12, and so on. If you had quarterly, that would be 4. Yeah, daily, that'd be 365. That's how many times you are applying the growth in each year. And then time is the number of years. Now, if you are trying to compound continuously, then we need to bring in the natural base of E. So that amount is going to be the principal times the base of E raised to the power of rate times time. That spells the word PERT, so that's one way to help memorize that. All right, let's look at a couple of details on the next page. Here are the examples, and there are the formulas again for your reference. You can take a look at those two there. Here's example number 5. So we have a financial example, and then down here in number 6 we have something that is not a financial example. So we can just kind of focus on the words that we're using as we're talking about the formulas. So here in number 5 we have $1,000 to invest. That's our starting amount at 8% for 10 years. So how much will the investment be worth if the interest is compounded monthly versus continuously? So we'll be doing two different calculations here because we have two different values for the amounts of compounding. Okay, so the principal is the $1,000. The rate is the 8%, but we always have to convert that to the decimal value. So remember, take your decimal point and move it 2 spaces to the left. So it looks like 0.08. The N here, in this case for monthly, that'll be 12. And the time frame that we're talking about is 10 years. So let's use our compounding interest formula. The amount is equal to the principal, that's 1,000, times the 1 plus. We want the rate over the N, so the rate is 0.08 over the 12. All of that is raised to the power of N times T. So N again is 12, and the T is 10. So we're just typing that in our calculator, of course. But a word of warning, I find that sometimes my students get the wrong answer even though they set it up right. And I think what might be happening is here in the exponent, how you type that in, maybe you need an extra layer of parentheses to communicate that both of those numbers are in the exponent. Sometimes your calculator will think just the 12 is the exponent and the 10 is not an exponent. So maybe turn that into 120 or wrap it in parentheses. All right. Since we're measuring dollars and cents, we want only 2 decimal places. We don't need 3 here, so there you go, 2,219.64 cents. What if we compound it continuously? That's where we need the natural base of E. So it's the principal times the base of E raised to the power of rate times time. So that rate is 0.08, and the time frame is still 10 years. So sure enough, you can see that you earn slightly more money, and that's because you are compounding more frequently. And that's what the base is representing. So in our financial formulas, we called this the principal, right? That's what our P was, but it's the starting amount. You could describe it as that way, or you could call it the initial amount, right? Those are some words that we use to describe what you begin with. And that's helpful when you think of situations where you are measuring other things, like in this case, we're measuring grams instead of dollars and cents. Let Y represent the mass of a particular radioactive element whose half-life is 25 years. That's what you see here in the base. The base is 1/2. That means we have exponential decay because that base is less than 1. So after a certain number of years, t years, the mass, the weight in grams is given by, so the mass in grams is, well, here's your little calculation. So what does this 10 represent? Right? That's what we were identifying here in the financial formulas. That starting amount is your principal. But this, we don't call it the principal, we call it the initial amount. Right? What is the initial amount of mass? Well, there it is, 10 grams. Now, if you wanted to plug in 0 for t, you could still work it out. It would look something like this. There it is, I'm dropping in 0 for 25. So if we're measuring, our time frame is 0, that means right at the beginning. No time has passed just yet. And so that means for us that we have an exponent of 0. Okay, what is a base to the power of 0? Just 1s, and 10 times 1 is 10. So sure enough, you can see that the initial amount is certainly what we end up with. So in this case, you can just observe it right from the equation. Okay, let's say 80 years goes by. Now, how many grams do we have left? Well, in this case, we're going to drop in 80 for the time frame. Right, there's your exponent, 80 over 25. Well, throw that at your calculator, right? I'm going to 3 decimal places, and that's in grams. So not very much is left. Compared with the initial amount of 10 grams, now we have 1 and a little bit left over.